Hello, let's continue our third optional lecture on grant and particularly some of the mathematical aspects of grant. So let's recall where we were at the last point. So we were considering this error exponent where, if you recall, the behavior that we were seeing here is basically related to the probability of error. So we have that the probability of error is decreasing exponentially with this quantity here that we named rho for the sake of ease of expression. So it's e to the minus rho, where rho is positive, n. So basically we have this exponential decrease, which, as we mentioned, is basically a way of looking at error exponents. We're not going to look at it here, but I would urge you to, if you're interested, read the paper with Ken Duff and Jen Lee on grant, because it presents not just error exponents, but it also presents a very interesting issue, which is that of success exponents. Success exponents occur when the rate is not below capacity. So remember, this is our capacity in the binary case. I've been thinking of taking everything log best A, so even if the channel is now binary, but over our larger alphabet, the 1 here corresponds to 1 log base A, and the H again here corresponds to a log base, the cardinality of A. So this here on the right is capacity, which is the maximum mutual information between the input of the channel and the output of the channel. So this is capacity. Okay. And you can also find success exponents, which means that if the rate is greater than or equal to 1 minus h and lower than some other quantity, which I'm not going to explore here, but again, if you're interested, I urge you to look at the reference. Let's call it R prime here for the time being. If R is between this, which is capacity, and some R prime, actually what will occur is that even though the probability of error is not going to be bounded away from 0, you can actually find that the probability of error is going to be not so bad as long as the number of guesses is not very high. So in effect, what happens is even if I'm operating above capacity, but not too much above capacity, then what you observe is that if I made a guess in the grand decoding that's fairly rapid, the probability that my decoding is still correct is actually still quite good. This is a very interesting behavior to consider. It's in effect highly non-standard with respect to traditional information theoretic approaches to transmission above capacity. Often transmission above capacity is avoided like the plague. And you have measures such as outage probability, which is the probability in some systems, particularly time-varying systems, such as wireless systems that may experience fades. Outage capacity is probably going below capacity. It's generally considered to be, in effect, catastrophic. What grant tells you is that if you decode with grant by guessing the noise, and if the noise effect, and if the noise effect is found fairly quickly, your confidence that your decoding was correct is still quite good. Because sure, maybe your rate's a bit too high, but if the noise was low, you probably still managed to hit the correct code word before hitting one of the incorrect code words. That is to say, if your rate is somewhat higher than capacity, then it is true that you're not guaranteed with high probability in this error exponent way to hit the correct code word. However, unless you're really a lot above capacity, it's still very likely that you will guess the noise N before you guess one of the code word difference noises corresponding to the code words that were not transmitted. So the probability of this happening may not be going exactly to 1, but it may still be very, very high. This is one of the reasons also why considering maximum likelihood decoding in the context of grant not only allows you to obtain results, much more elegantly than maybe you could have with traditional array of exponents, but it also allows you to obtain results that would be extremely difficult to obtain, and actually up until now have not been obtained in the case of traditional code-based decoding. So think of this aspect here as being really, really the crucial aspect, which is guessing the noise before guessing the code word difference noise. This really indicates that guessing the noise, the correct noise, is fairly robust. Again, unless you have such a plethora of code word difference noises that it becomes highly likely that the minimum of those guesses will come before the guess of the actual noise. Okay, so let's look at what this actually is telling us as to how many guesses we would have to do. Here is a representation of the probability that actually the number of guesses per bits in a layer, and this is how much guesswork we have normalized by the number of bits. So here, what do I have? I have in white, I have the typical set. Here I have 99 probability of 99.99, and here is I have the average guesswork if I had to guess the actual noise. Okay, and what we see here is that you hit the typical set fairly quickly, and with a number of guesses per bit. That's to say, how many guesses do you have to achieve until you guess to that entire layer of noise possibilities, which is really quite low. I'd like to highlight this. It's really quite low. You're really looking at order 1. This is for a bit flip. This is for a code length of length 75. At bit flip probability in my binary symmetric channel of 10 to the minus 2, a code rate of 0.72, okay? This is with a probability of block error rate of 10 to the minus 3, okay? So lower than my raw bit error probability. And this is with a probability of abandoning of 0.001. So you can see that I will actually hit the typical set way before I abandon, right? Because basically this is where I'm abandoning. This is my probability of abandoning, because I'll abandon after this amount of time. So I hit the typical set way before I abandon. I still have, with this typical set here, so this is the typical set, I still have really a very good block error probability, Okay, another way to look at it is in terms of probabilities, in terms of a CDF, where here you see the cumulative probability. You have accumulated some probability. Here I have accumulated all till I finish the typical set. Then I have here basically this is, by the way, I'm using except for the typical set in white and the probably 0.99 in turquoise. I'm really using a heat map, okay, and the black here for guessing the average number of trials, guesses to guess the actual noise, which is this one. What I'm doing here is I'm using a heat map. So the purple here is because I've only accumulated about 0.5 of the probability. Red is because I'm basically at 1. Okay, so what you see here is that we've really accumulated almost all, that by the typical set, which is happening right here, I'm basically done. And this probably 0.99 is happening right here, right? This 0.99 is happening right here. Okay, and here's the CDF of the whole thing. So basically what we can see, so again, blue means 0, red means close to 1. What we can see is that we have a behavior which indicates that with very few guesses, I am basically able to get a really already very good probability of error. Let's look at another example. So in this example, I'm now looking again at a binary symmetric channel, so Bernoulli noise. And you can see a little bit more differentiation here. You can see this heat map of accumulating probability from blue to red. Purple is kind of like around 0.5. Here again, you see the Shannon typical set. Here you see probably 0.99. And here you see what it would actually take for you to guess the real noise. So you can see that guessing the real noise on average takes a long time. Why? Because some of the noises are atypical and take a really, really long time to figure out. But those noises, I'm never going to get to. Why? Because either I'm just going to give up because of I'm going to give up in the channel typical set. I'm just not interested in them. Or because I actually am going to hit a code word difference noise before I get to these really weird noise sequence occurrences where I will then end up having a huge number of guesses before I guess these unusual noise sequence effect occurrences. Okay, so basically, again, almost all the probability is going to be captured here in the set of size to the n h plus delta, even though h, as we mentioned, the Shannon entropy, is less than the Renyi entropy of order 1/2, which is what would actually be required. In order to guess the exact noise. But remember, we're not worried about the exact noise effect. I'm not really worried about the noise effect per se. I'm only worried about it as it helps me to decode beyond a certain level, which is, either beyond the typical set, so beyond my probability of error, which I'm designing my block error for, or beyond the probability that I'm already going to hit a code difference noise, so that I'm going to make an error. I don't actually need to worry about whether I'm guessing the actual noise or not. So going back to my error rates, here, what we have is that if this error rate and for the noise, this probability rate, not error rate. This rate here for the noise does have a derivative such that for some value of x, which we're denoting by x star, it's equal to 1. Those of you who are familiar with error exponents will see the resemblance between this and some of the error exponent description. If you have never seen those, don't worry about it. This doesn't need that background. Okay. Then the error rate is actually going to simplify to the following. So this error rate epsilon of r is going to simplify to the following. Again, remember that this over here is the probability of error. Okay, this is probability of error. So this probability of error here, okay, this is the error rate in terms of the rate, is going to have the following behavior. It's going to be in 1 minus r, as far as in this range, which is, this is below capacity, okay? And if it's in this other range, it's actually going to go down like this, where actually what this means is that we have, in both cases, we're going to have a system where the error rate here is negative, but it has a somewhat different behavior in these two regimes. Okay. This in 1 minus r here for all in this range, this is going to be negative. And let's just do a very quick sanity check on what's happening here on this quantity here. Okay, let's do a quick sanity check. So remember that r is the rate is going to be less than 1 minus h. Okay. So what does that mean? 1 minus r. Okay. 1 minus r is going to be greater than h. And recall that h here, recall that h is less than h sub a half. I'm going to call it h1/2. Okay. So because of this, what do we have? We have that 1 minus r, which is greater than h. Okay. And then I have something which is going to be less than h1/2. So this behavior here, we're going to have 1 minus r. So if I subtract h1/2 from both sides, I'm going to have that 1 minus r h1/2, okay, is actually going to be greater than h minus h1/2, okay? All right, what is happening here? When my, because remember that h is less than h1/2, h minus h1/2, okay? This is just going to be negative, okay? So all we know here is that this is something larger than something negative. It's actually showing that my guessing for these kinds of rates is just having a somewhat different. It's just going to have a somewhat different behavior, which is going to be depending on this difference. Or recall that there's something interesting happening here on the cutoff rate, because 1 minus h 1/2 cutoff rate. Okay, so there's something a little funny happening here between between R and the difference between R and the cutoff rate. Okay, this is the cutoff rate minus R. That's what this is. Okay. But the main point is that this is what the error rate is. And moving on to the next slide. Moving on to the slide, what I'd like you to remember is the following. This is, as we saw before, the exponent, the rate for the minimum of the guesses among all of the code word, noises that would correspond to going to a different code word. So this is the code word difference noises that we spoke about. This here in red is actually the behavior of the exponent for the guessing of the true noise. Okay. At some point, I'm more likely to have guessed the code word difference noise than I am to have guessed the noise. Okay, here we're seeing a behavior that's going with h 1/2, which would be guessing the actual noise. Okay, and think of this in terms of a approximation where, harking back to what we did in the first lecture with typical sets, this is something where the behavior is similar to what's happening in a typical set. We're looking at the probability that the guessing approximates some number to the nx is itself approximately this quantity, okay? And here, the probability that the guessing of the code of the first code word difference noise takes approximately to the nx is approximately the exponent of this. Okay, so remember what we did in the first lecture with the typical set, where we had a probability being in a typical set, which was roughly 1, but there was this exponential behavior in the size of the typical set. And also in the approximation to 1 that we explored. So we're seeing the same sort of behavior here. It's just a behavior that's done with a little bit more subtlety and a little bit more granularity, okay? But this is really the behavior that I want you to think of is happening, okay? The behavior that's happening here is this one, okay? All right. This behavior here is what's showing in how many guesses it's going to take me to get the noise. So this one here corresponds to this curve. Okay. And this one here is corresponding to this curve. So you can see these two curves basically representing these two behaviors. At this point over here, what's happening at this point over here, this is basically where I no longer care about guessing the noise because I'm already with high likelihood guessed the code word difference noise. There's no point in keep keep guessing, I'm not going to guess the noise at that point. I will have with high likelihood guess the code word difference noise. So what is the trick? The trick is that here, which is what's at H, which is where the typical set is happening, here is where I'm highly likely to have finished decoding. Okay, this is where I'm highly likely here's when I'm highly likely finished coding right here. Okay, so where I'm highly likely to have finished decoding, as long as that happens before I'm highly likely to have hit the code word difference noise, then I'm okay. So this point here has to happen to the left of this point here. So here I'm highly likely to have finished decoding. Here, on the other hand, I'm highly likely to guess the code word difference noise. Okay. And that's what's happening. All right. So that's the race between guessing the correct noise and guessing the code word difference noise. And as we said here, almost all probabilities captured by sequences in the Shannon typical set, which is of size to the NH, okay, which is happening right here, even though H is less than H1 half, which is happening somewhere here. All right. Okay. So that's why, by the way, here I'm really not looking at the structure of the code and the types of developments that have happened in coding, you know, for many, many years, from block codes, evolutional codes, so-called block margin codes, or the LDPCs have been knocking around since the early 60s, turbo codes, you know, small block size polar codes, CRC-aided polar codes. All of those have always had their encoders and their decoders co-designed. We don't actually need to do that. Okay, so I hope that this second part of the third lecture was helpful for those of you who are interested in delving a little bit more deeply into the mathematical structure and the behavior of decoding with grant, and particularly this race between two types of error of guessing noise effects, the real noise and the code word difference noise. The next lecture, which is also optional, but I think many of you will be interested in, given the set of questions I've already received, the next lecture will be on using soft information. So far, we've still looked at noise as being a digital effect. We'll look later at noise being a non-digital effect. Thank you.